When installing parallel conductors to compensate for voltage drop, the National Electrical Code, specifically Article 250.122F, dictates the size of the grounding conductor. The question is whether these parallel conductors are treated as increased in size per 250.122B or as conductors in parallel per 250.122F. In installations where parallel conductors do not exceed 3 in number and are not installed in separate raceways, the grounding conductor must have an ampacity not less than the largest of the parallel conductors. In the provided scenario, the conductors are considered conductors in parallel because they are used to compensate for voltage drop. According to 250.122F, the grounding conductor must have an ampacity not less than the ampacity of the largest parallel conductor, which in this case is 3/0. Therefore, the minimum required grounding conductor size is 3/0. It is vital to install the grounding conductor in the same raceway as the parallel phase conductors. The grounding conductor should be sized appropriately to handle the fault current that may flow through it. In some cases, a larger grounding conductor, such as a 350 kcmil conductor, might be a better choice to ensure proper grounding. Here's a deeper dive into the requirements and considerations. Firstly, let's clarify the difference between increasing conductor size for ampacity versus paralleling conductors for voltage drop. When conductors are increased in size for ampacity, you would refer to 250.122B to determine the size of the equipment grounding conductor. However, in the scenario described, the conductors are paralleled specifically to address voltage drop over a long distance, approximately 550 feet. This distinction is crucial because it leads us to apply 250.122F, which deals specifically with conductors in parallel. Secondly, the rule in 250.122F is very clear if the parallel conductors are installed in the same raceway or cable. In this case, where you have two sets of 4 3/0 conductors in a 3-inch PVC conduit, the equipment grounding conductor must be sized based on the ampacity of the 3/0 conductor. Table 310.16 in the NEC provides ampacity ratings for conductors. For example, a 3/0 copper conductor with type THHN insulation, which is commonly used, has an ampacity of around 200 amps when installed in a raceway and operating at a 75 degrees Celsius temperature rating. Since you have two sets of these conductors, the total ampacity is significantly higher, but the grounding conductor size is based on the individual 3/0 conductor. Thirdly, an important consideration is the fault current. While 250.122F provides the minimum size for the equipment grounding conductor, it is imperative to ensure that this conductor can adequately handle the available fault current. A short-circuit study of fault current calculation will determine the magnitude of the fault current at the 225 amp panel. This calculation takes into account the source impedance, conductor impedance, and any other impedance in the fault current path. The equipment grounding conductor must have sufficient ampacity and be properly sized to withstand this fault current without exceeding its temperature rating. Fourthly, let's discuss practical considerations for installation. The equipment grounding conductor should be installed in close proximity to the circuit conductors. This minimizes impedance and ensures a low impedance path for fault current to return to the source, which facilitates the quick operation of overcurrent protective devices such as circuit breakers or fuses. In your specific setup with two sets of parallel conductors in a 3-inch PVC conduit, you should run the equipment grounding conductor inside the same conduit to comply with this requirement. Fifthly, consider the material of the grounding conductor. While copper is a common choice, aluminum can also be used, provided it meets the NEC requirement. Aluminum grounding conductors must be sized larger than copper conductors to achieve the same ampacity. For example, if a 3/0 copper conductor is required, an equivalent aluminum conductor would need to be larger to meet the same ampacity and fault current handling capability. Sixthly, grounding electrode conductor versus equipment grounding conductor. It is essential to differentiate between the equipment grounding conductor and the grounding electrode conductor. The equipment grounding conductor connects non-current carrying metal parts of equipment to the system grounded conductor or the grounding electrode conductor, ensuring a low impedance path for fault current. The grounding electrode conductor, on the other hand, connects the system grounded conductor to the grounding electrode system, such as ground rods, metal water pipes, or ground rings. In your scenario, we are focusing on the equipment grounding conductor that runs with the parallel feeder conductors. Seventhly, the importance of proper terminations. Proper terminations are crucial for effective grounding. Ensure that all connections are clean, free of corrosion, and properly torqued to the manufacturer's specifications. Loose or corroded connections can increase impedance and reduce the effectiveness of the grounding system. Use appropriate connectors and tools to make these connections. Eighthly, documentation and labeling. It is good practice to document the size and type of the equipment grounding conductor in your electrical drawings and panel schedules. Labeling the grounding conductors and terminations can also help during future maintenance and troubleshooting. Ninthly, coordination with overcurrent protection. The equipment grounding conductor must be sized in coordination with the overcurrent protective devices. The goal is to ensure that the grounding conductor can safely carry the fault current long enough for the overcurrent device to operate and clear the fault. This coordination is crucial for electrical safety and preventing equipment damage. Tenthly, revisiting the 350 kc mil suggestion. The initial suggestion of using a 350 kc mil grounding conductor was to emphasize the importance of considering fault current. While a 3/0 grounding conductor meets the minimum requirement per 250.122 F, a larger conductor like 350 kc mil could provide a lower impedance path and better fault current handling capability, especially in systems with high available fault current. This decision should be based on a detailed fault current study and engineering judgment. 11thly, voltage drop calculations. The original reason for using parallel conductors was to address voltage drop. It's essential to verify that the parallel conductors adequately mitigate the voltage drop to within acceptable limits. Voltage drop can affect the performance of equipment and can also lead to overheating of conductors and equipment. The NEC recommends limiting voltage drop to 3% for feeders and 5% for the combined feeder and branch circuit. 12thly, conduit fill considerations. When installing multiple conductors in a conduit, you must adhere to the conduit fill requirements specified in Chapter 9 of the NEC. The number and size of conductors allowed in a conduit depends on the conduit size, conductor insulation type, and other factors. Ensure that your conduit fill calculation complies with the NEC to prevent overheating and damage to the conductors. 13thly, the role of a licensed electrician. All electrical work should be performed by qualified and licensed electricians who are familiar with the NEC and local electrical codes. Electrical work can be dangerous, and improper installations can lead to electrical shock, fire, and equipment damage. A licensed electrician has the training and experience to ensure that the installation is safe and compliant with all applicable codes and standards. 14thly, the impact of harmonics. In systems with significant harmonic currents, the equipment grounding conductor may need to be sized larger than the minimum required by 250.122 F. Harmonic currents can cause overheating of the grounding conductor and can also interfere with the operation of sensitive electronic equipment. If harmonics are present, consult with an electrical engineer to determine the appropriate grounding conductor size. 15thly, surge protection. Consider installing surge protective devices, SPDs, to protect sensitive electronic equipment from voltage surges caused by lightning, switching transients, or other sources. SPDs should be properly grounded to provide a low impedance path for surge current to ground. The equipment grounding conductor plays a crucial role in the effectiveness of SPD. 16thly, ground testing. After the installation is complete, it is a good practice to perform ground testing to verify the integrity of the grounding system. Ground testing involves measuring the ground resistance and impedance to ensure that they are within acceptable limits. High ground resistance can indicate a problem with the grounding system, such as corroded connections or inadequate grounding electrodes. 17thly, regular inspections and maintenance. Grounding systems should be inspected and maintained regularly to ensure their continued effectiveness. Inspections should include checking for loose connections, corrosion, and damage to grounding conductors and electrodes. Any problems should be corrected promptly to maintain a safe and reliable electrical system. 18thly, the NEC is a living document that is updated every 3 years. It is essential to stay current with the latest edition of the NEC to ensure that your electrical installations comply with the most up-to-date requirements. Changes to the NEC can affect grounding requirements, so it is important to be aware of these changes. 19thly, local amendments to the NEC. Many jurisdictions adopt the NEC with local amendments that may add, delete, or modify certain requirements. It is essential to be aware of any local amendments that apply to your area and to comply with these requirements. Local amendments can vary significantly, so it is important to check with your local electrical inspector. 20thly, the importance of training. Electrical work requires specialized training and knowledge. It is essential to invest in training for electricians and other electrical workers to ensure that they have the skills and knowledge necessary to perform their work safely and effectively. Training should cover topics such as grounding, bonding, overcurrent protection, and electrical safety. 21st, bonding versus grounding. Bonding and grounding are related but distinct concepts. Bonding involves connecting non-current carrying metal parts together to create an electrically conductive path. Grounding involves connecting the bonded system to the earth. Both bonding and grounding are essential for electrical safety. 22nd, ground fault circuit interrupters, GFCIs. GFCIs are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. The equipment grounding conductor plays a crucial role in the operation of GFCIs. 23rd, arc fault circuit interrupters, SIs. SIs are designed to protect against fires caused by arc faults. Arc faults can occur when there is a break or weakness in the insulation of a conductor, causing a spark or arc. SIs are required in many locations, such as bedrooms and living rooms. The equipment grounding conductor can help to reduce the risk of arc faults by providing a low impedance path for fault current to return to the source. 24th, isolated ground systems. In some applications, such as sensitive electronic equipment, it may be necessary to use an isolated ground system. An isolated ground system is a special type of grounding system that is designed to minimize electrical noise and interference. Isolated ground systems require special wiring and grounding techniques. 25th, electrostatic discharge, ESD. ESD can damage sensitive electronic equipment. To protect against ESD, it is important to use proper grounding and bonding techniques. ESD control measures include wearing wrist straps, using grounded work surfaces, and controlling humidity. 26th, lightning protection systems. Lightning protection systems are designed to protect buildings and equipment from lightning strikes. Lightning protection systems include air terminals, down conductors, and grounding electrodes. The grounding system is a crucial part of a lightning protection system. 27th, the role of the electrical inspector. The electrical inspector is responsible for ensuring that electrical installations comply with the NEC and local electrical codes. The electrical inspector will typically inspect the installation at various stages of completion and will issue a certificate of occupancy once the installation is approved. 28th, the importance of communication. Effective communication between the electrical designer, the electrical contractor, and the electrical inspector is essential for a successful electrical installation. Regular meetings and clear communication can help to avoid misunderstandings and ensure that the installation is compliant with all applicable codes and standards. 29th, the use of software for grounding calculations. There are many software programs available that can help with grounding calculations. These programs can automate the calculations and help to ensure that the grounding system is properly designed. 30th, the importance of continuous learning. The field of electrical engineering is constantly evolving. It is important for electrical engineers and electricians to engage in continuous learning to stay up to date with the latest technologies, codes, and standards. Continuous learning can include attending seminars, reading technical publications, and participating in online forums. In summary, grounding parallel conductors requires careful attention to the NEC, particularly 250.122F. While the minimum size is determined by the ampacity of the largest parallel conductor, additional factors such as fault current, harmonic currents, and voltage drop must be considered. A thorough understanding of these concepts and adherence to best practices will ensure a safe and reliable electrical installation.